Okay, so I'm gonna start filling in the notes here, but I want you to wait on this drawing it because I'm gonna do some things and then have to erase them. So what we're gonna first graph is y equals the inverse sine of x. So there's another way of saying that, and that's called arc sine. You sound pretty cool when you say the word arc sine instead of saying inverse sine. Arc sine just makes you seem like you're in some advanced math. So the reason that you choose arc sine versus the -1 symbol is because the -1 may look like an exponent and it's not an exponent. It's just a symbol for inverse. And what that means is you switch the x's and the y's. So just as a reminder, like if I do arc sine x, this, what I'm plugging in is the ratio is getting plugged in and it equals the angle coming out. So, wait, in case we're wondering what the pieces represent. So what is going to happen is we're going to switch the x's and the y's, and let's think about the graph of sine, the wave of sine, that would normally go like this, but now pretend the x's and the y's have been switched. So the y-axis usually was from -1 to 1, but now it's the x values are from -1 to 1. And then the x-coordinates, which were usually from 0 to 360 or 0 to 2 pi, are now the y values here. So 0, let's say this is pi over 2. Let's get to pi right here. And I'm actually going to need a little, maybe I'll just don't draw this yet, but 3 pi over 2 would be like right here. So let me see if I can draw the sine wave kind of on its side here. So it originally started at the origin, 0, 0. Then at pi over 2 is when it went up to 1. And then at pi, it went back to 0. So the first half of the wave would look like this. Like that. Okay, well, instantly I see a problem with this graph. And I haven't even finished it completely. I don't know if you can see what the problem is. Yes, that's right. The function does not pass the vertical line test anymore. It would not pass the vertical line test. So we have an issue forming here where we can't make this a function if it doesn't pass the vertical line test. So what we're going to do is I'm going to continue this function wave going into the negatives, so negative pi over 2, negative pi, and it would go like this, which clearly makes it even worse as far as passing the vertical line test. But what I'm going to do is create some restrictions on this wave. I'm going to change my range here so that it does pass the vertical line test and captures every ratio between -1 to 1. So here's what I'm going to do, and this is just the way that we've all decided would make most sense to keep these pieces of the graph. Of course, I could have erased other pieces, but this just would make the most sense, is to keep just between here and here. So this part of the wave, it's like, it doesn't even look like sine anymore, but yet it still captures all the ratios from -1 to 1, and it passes the vertical line test. And that is the graph of the inverse of sine. It has been restricted because it can't, it has to pass the vertical line test. So here's what the restrictions are. So let me say this, for the ratios are here on the x-axis. The ratios are all there, as normal, are from -1 to 1, and they touch, so there's brackets there. Now the angles, which are the answers, if you want to make a note that that's the answers, you can. The angles that I can give as an answer are only from -pi over 2 up to pi over 2. And they do touch it, so brackets on that. Now, in addition to that, I'm going to just say what this range represents if we were to look at a unit circle. So starting at negative pi over 2 is the lowest point. So negative pi over 2 would mean you move negative in this direction to half of a pi. So this is where we start. Let's pretend this is the beginning. And we have to go all the way up to pi over 2. So starting here, going bigger values to 0 and then up to a positive pi over 2 would mean I'm going between here to here, leaving my restrictions between anything in quadrant 4 and then in quadrant 1. So I'm going to just, in addition, put Q1, Q4 are these spots here. Now, I know some questions sometimes people have are, well, wait, why this graph's not in Q1 and Q4, it's in Q1 and Q3. It's because this is not the unit circle graph. So this is from the unit circle. This graph is just kind of to get a visual of why this stuff has to happen. All right, so there's the inverse sine. Let's do the inverse cos or arc cos. So as before, we're switching the x's and the y's. So now this becomes -1 to 1. And then we have 0, pi, 2 pi, half pi, and 3 pi over 2. And here's how cosine's iron condor would look if I switch it on its side. So the iron condor starts at 1, it ends at 1, and then right down the middle is when it's at the bottom of the wave, and then it hits the center right down the middle here. And then back. Okay, but clearly the iron condor on its side does not pass the vertical line test. So we're going to have to eliminate some of this graph so that it captures everything from -1 to 1, but yet still passes the vertical line test. So the way that would work for that is if we erase this top portion here. And now I got from -1 to 1. It doesn't quite look like cosine anymore, but that still does it. All right, so there's our new restriction. So the ratios here, as we want them to be, the ratios fit anywhere between -1 to 1, as they should always. And then the angles for this problem are a little bit different angles. So the angles start at 0 at the smallest and can go all the way up to pi at the largest. If you look on the unit circle, what quadrants that would represent on the unit circle, starting at 0 to pi would be the first and the second quadrant here. So Q1, Q2. Okay, now lastly is tan. And tan's, remember that typically goes like this shape, is now going to be on its side. So I'm going to mark off 1 and -1 here. And pi over 2 here, -pi over 2 here, because those points were kind of key. Those were the points where the asymptotes were at. They used to be vertical asymptotes. Now they're horizontal asymptotes. There were then points at pi over 4 and -pi over 4. Those values were when it was +1 and -1. And then the origin was at 0, 0. And so it was like kind of like a half parabola this way, half parabola this way. And there's the graph of tan on its side inversed. Now this repeats this shape up above here over and below here over and over again. But if I drew it a second time up here, then it would not pass the vertical line test. So this region is perfect then for us. It passes the vertical line test and it captures all the ratios, which the ratios for tan are not limited to -1 to 1, but from -infinity to +infinity. And that's because tan's ratio doesn't have a hypotenuse like cosine and sine did, because with sine and cosine, the hypotenuse always had to be the biggest side. That's why the ratios were like limited to 1 and -1. the hypotenuse had to do that, but not with tan. So the ratios here can be, there's any value between negative infinity to infinity. And then the angles are limited to anything at the lowest would be negative pi over 2 to pi over 2 at the highest angle. Now I'm putting parentheses on these because there are dotted lines here as the asymptotes. So there are limited here between negative pi over 2 and pi over 2 is on the unit circle is at the starting at the lowest is at negative pi over 2 would be right here. So that's the first value. And then as we go up through 0 to positive pi over 2, it would limit us to quadrant 4 and quadrant 1. Okay, now let me just do one example, just quick idea then of how these like restrictions matter. So let's say I was doing a problem here before I get to the notes. Let's say I was doing a problem that was sine inverse of 1/2, and I needed to find that, which is an inverse function, means I can only get one answer. So I look on my unit circle and I find the ratio where it's 1/2 for sine. And that would be the y coordinates. It would be right here. So that in degrees would be 30 degrees. X would equal 30 degrees. Now there's also another time when sine is 1/2, that's over here, which would be 150 degrees. But if you notice, then 150 is in Q2, but Q2 is not okay. Our angles have to be within Q1 and Q4. That's why on the calculator, you will not get that answer, but you'll get the answer from Q1. Let me do another one like that. This time, I'm going to do negative 1/2. And this time, yeah, I'll do it in degrees for now. So for this angle at negative 1/2, I'll look on the unit circle, and negative 1/2 y value is here at 210. But 210 would be in the third quadrant, and our restrictions say it cannot be in the third quadrant. So this is not the answer that the calculator is going to give. So there must be another one. The answer I can see also is negative 1/2 at 330 degrees. Now this is where it gets a little confusing. So 330 degrees seems like the answer, but 330 is in the fourth quadrant, but notice the angles had to be between negative and positive pi over 2, which is, in other words, negative 90 degrees and positive 90 degrees. 330 is not within negative 90 to positive 90. So 330 is the location, but it's not the answer we would give you. So how could I get to 330 by using a negative angle? Well, you just have to go negative 30 degrees. Negative 30 is the answer. Not this. So if I put it in my calculator, for inverse sine of negative 1/2, I should get negative 30 out of the answer, not 330. There it is. So the answers are always still going to be like, 30, 60, 45, but they might be positive or negative in this case.